Hello everyone, today we will verify the KVL or Kirchhoff's voltage law. So before going into the experimental setup, we will first talk about some theory. So the statement of KVL is the algebraic sum of all voltages around any closed loop is 0. So that mathematically we can write summation of V equals 0. So this is a closed loop, and in this loop we have supplied a voltage from the voltage source to resistors. We have taken a simple circuit, and in this circuit resistor 1 is 50 ohm and R2 is 10 ohm. So from the statement of KVL, summation of all voltages is 0, we can write this. So from that we see there are three voltages we can find. At first the voltage source is applied and the voltage across resistor 1, resistor 2. Okay, so now we have written here minus V plus V1 plus V2. This is a sign convention, we can take it anyway. In this explanation we have followed the first sign of the voltage. So here is the minus sign and here is plus sign. We start from the first sign. So minus V plus, from this resistor this one we can say this is plus V plus and this is minus. Okay, so from this part we can write plus V1 because this resistor voltage drop starts with a plus sign. Same for this resistor, this is plus and this is minus. So we can write minus V plus V1 and plus V2 equals 0, and from that we can write V equals V1 plus V2. We can also say from this mathematical equation that in KVL the voltage rise equals voltage drops, because we have seen that this is the only voltage rise or the supply in this circuit and these are the voltage drops. So we see V equals V1 plus V2, the supplied voltage equals voltage drops. Okay, so we can mathematically now calculate that. We will see what is the voltage drop across V1 R1 and voltage drop across R2. So we will find V1 equals V into R1 divided by RT. This is where this is what we applied voltage divider rule. So the voltage into the resistor and total resistor. Okay, so 10 into 50 divided by 60, we got 8.33, and same way we applied voltage divider rule for this resistor and we find voltage 1.67 volt. So if we sum these two, we will find 8.33 plus 1.67 equals 10. So we find that our voltage drops equal supplied 10 volt. Hence we see this is the mathematical proof of KVL. So let's get into today's experiment, verification of KVL, that is Kirchhoff's voltage law. To conduct this experiment we will need some apparatus, that are multimeter, we need 3 rheostats, 1 SPST switch and a DC power supply. And if we look at the circuit diagram, we see there is a voltage source and the voltage source is connected to a SPST switch. SPST switch is connected to 3 rheostats in series. So we will measure the voltage source, so how much voltage you have supplied to the circuit, and then we will measure the current flow in the whole circuit, and individually we will measure the voltage drop across each resistors, and we will verify the KVL. So let us get into the circuit connection. Here we have our DC power supply. We can supply 0 to 30 volts and 0 to 3 amp from this power supply. We have one SPST switch and we have 3 rheostats here. Here is our multimeter we will use to measure the voltage and currents. From the first point we see our voltage supply. So the positive part of our voltage supply is given to the pole of SPST switch. So this is our positive part and we will connect it to the pole of our SPST switch. So we will connect it here. We'll connect it here, and then we will connect the throw of our SPST switch, to the rheostat 1 or the first rheostat. So we will connect we'll connect this SPST switch to our first rheostat. Okay, and then we will, okay, let me rotate the phone. Then we will see that the second part of our first rheostat will go to the first part of our rheostat 2. So we will take a wire and we connect it from the ending or the second part of first rheostat and connect the wire to another rheostat. So we got it here, and then we connect the second part of our rheostat to the first part of our third rheostat. And we see at the ending of the rheostat 3 is connected to the negative of voltage source. So this is our negative of the voltage source. Negative of the voltage source that is connected to the end of this rheostat. So let's recheck our circuit connection. The positive of the voltage supply will go to the pole of the SPST switch. The throw of the SPST switch will go to the rheostat 1, and the end of the rheostat or the second part of the rheostat 1 will go to the rheostat 2 first part. Here is our first part, and the second part of the rheostat 2 will go to the third resistor's first part or third rheostat's first part, and the ending of the third rheostat will go to the negative of the circuit of the voltage supply, and the circuit is completed. So now we will give supply to our circuit. We'll turn on the voltage source. We see that we are getting 14.6 volts now, so we will give it 15. Okay, we are making some fine. Okay, fine. So we are giving 15 volt supply. Now we will measure the current flowing in the whole circuit. For measuring the current, we need to measure it across the switch. So here we can see that the amps is connected parallel in the switch, but it is not actually like that. If we connect the ammeter across the switch, it will actually behave like an ammeter. It will actually measure the current, because if we turn off the switch and connect the ammeter across 2 points of the switch, that will be in series connection and we will get the measurement of current. So let's do it. For that, we have to turn on our multimeter first and take it in the milliamps part. So we have rotated the knob to milliampere, and now we will measure the current across the switch that is flowing in the whole circuit. For measuring current, we must turn off the SPST switch, otherwise it will create a short circuit. So I will put it here, the first part, so it is a bit difficult. I will put the phone somewhere else. Okay, I think now we have a better view. So we will see that our multimeter is now in milliamps, that is here we see the parameter is in milliamps. Now we will measure the current through SPST switch. So for that we have turned off our SPST switch, so that we can see that is turned off. Now we will measure the current, so we can do it. Now we see our multimeter is showing some value, that is 16.47 milliamps, we can say 16.47 milliamps. So now we will write that value in our data table. We will give the value here. Our current flowing is 16.47 milliamps. Okay. The second thing we will do is measuring the voltage across the three resistors we have here. So the first time we will measure the voltage across this resistor, that we have take this one as resistor 1 or rheostat 1. So we will measure voltage drop across this rheostat. So for that we have to take our multimeter in voltage, and we have rotated our knob to voltage measurement parameter. Now we see that our range is millivolt. We will change the range from millivolt to voltage. Okay, so the main thing we want to do here is we will measure the voltages across three rheostats, and we will sum up the voltage drop of three resistors, and we see if we get the total voltage supply equals to the voltage drop across three voltages. If we get summation of three voltage drops equals the voltage supply you have given, then we can say the KVL is verified. So let me do that. The voltmeter is here, and we will measure voltage. So for the voltage measurement we must turn on the SPST switch, because we must have the current flow in the circuit. So we will measure the voltage across 2 points of the rheostat. Now we can see the voltage drop across the first resistor, our first rheostat is 2.69 volt. So we will write it down as well in the table. Voltage 1 was 2.69 volts. Okay, for the second rheostat we will follow the same process. Okay, so we will measure the voltage across rheostat 2, that is this rheostat. So what we see, that we have a voltage drop across rheostat 2 is 8.10 volt. I think that is visible in the camera. Okay, 8.10 volt. So we have written it down in the data table. Let me check again. 8.10 volt. And for the third rheostat we will do the same process. So if we measure the voltage here, so if we measure the voltage here, we see that we have got 3.95 volts across this rheostat. 3.95 volt. So now let's check. If we sum up these three voltages, if we sum up these three voltages across the three rheostats, we will measure, and we check if the voltage source we have supplied here is 15 volt, and the sum of these three voltages are summed as 15 volt. So if we sum up the voltages, we get 14.74 voltage. So I think that's fair, because at this moment we can see that our voltage supply is 14.9 volt, though we have started with 15 volt. So the voltage supply sometimes goes ups and down, so we can see some changes in our values, but we can accept 14.7 volt, and we will definitely see some difference between the supplied voltage and the measured voltage. So we have done it, and now we will check, and now we will check other things, that we will measure the rheostat values and we will sum up them, and we will put the value here that we will measure from our multimeter, that we have measured the rheostat values, and we will use the equation of Rs equals Vs by I, and we will check if the two Rs value matches or they are close. Now let us measure the rheostat value. We will do that by using this multimeter. For that we have to rotate the knob to the ohm sign, so we have brought it here, and we can keep the range in ohm, or we can select kilo ohm. I think I will go with kilo ohm, because in this experiment I would like to keep it here. So let us measure the first rheostat. So if we put the 2 points of the multimeter, we find 0.164 kilo ohm, 165 kilo ohm, that is okay, 163 is the fixed value, that is 160. For the second rheostat we will follow the same process. So 89 we will take 489 ohm. Okay, 489 ohm. And for the third rheostat we will follow the same process. 0.240 kilo ohm, that is 240 ohm. 240 ohm. So if we sum up, we will find, so we get 892 ohm. So we'll put the data in our data table. That is RS we measured here, R1 plus R2 plus R3 is 892 ohm. Okay, so we will now verify this by using the equation of RS equals Vs divided by I. So our Vs was 15 volt and I was 16.47 milliampere. So now we will use calculator and check if the calculation is correct. So let us use this calculator. So our voltage was 15 volt. So divided by current, we found our current 16.47 milliampere, that is 10 inverse 3 in amps. So we find our resistance is 910.74. So if we write it down here, 910.7 ohm, we can see that the measured value and the calculated value is just a bit different. So we can see that we are very close to the measurement, and we see that the voltage we supplied is 15 volt and we calculated across each rheostat is summed to 14.74 volt. So we see that is also very close. So we can say that there are always some losses and we will not get the exact value, and we can accept the close values. So there, hence our verification of KVL is proven.